All right. Your company must run Ethernet cables to 5 different offices so that all offices have high-speed internet access. And for each computer to be on the office network, there must be a way to get for each computer to the other computers by following the cable. All right. One worker proposed running a cable between the 5 offices as illustrated in the following diagram, and the vertices represent the offices. The edges represent segments of the cable. So, looking at this graph, how many lengths of cable or edges are used? And then I need you to explain why this is an inefficient way to run the cable. Now, that's the bell ringer. It's also question 1 on the assignment. Well, maybe not on the assignment, but on the assignment in the book. So, just think about it this way. Is there a way, looking at the offices being represented in this graph as the vertices and the cables going between the offices represented by the edges, is there a way where they can all be connected but be a little more efficient? That's what we need to think about, okay? So let's continue on real quick here. I usually do good things when I do this lecture, so the whole point here is to just explain to me what's good in your life. What I'll do, since we're doing these videos instead of the lectures in the class, if you have some good things to share with me, I'll definitely bring them up in class the next day. If you just send me a message via Google Classroom, tell me what happened great that's happening in your life. For instance, this weekend I got water plumbed to my one of my sheds, and I actually have a running sink now. It's the first time I've had water in my shed in 20 months. Now, if you know my story really well, you'll know that that's a big accomplishment. It only took 2 families and about 7 kids and me, all above the age of 13, digging a ditch. So, but if you know the land around here, that ditch is took a while. All right, so let's look at these 4 different designs here. I usually do finger polling when I do these in class. I'll have to fix these before next year. But determine which design is more efficient. In other words, which design uses the least number of cables but remains connected? Okay, so let's eliminate the ones that don't work, all right? So which ones are not connected? We can eliminate those. And then we'll look at all the ones that are connected. Are we using too many cables? Is it inefficient? Or are we using just enough? And in the cases where they're not all connected, are we not using enough? So I'll leave this one for you to take a look at. Okay, obviously I just gave you the answer. I didn't even realize it, but yes, 1 and 4 are both correct answers. Now there's a cool little tool to use here. If you count the number of vertices, in this case there's 5, in order for them to be efficiently connected, all of the vertices must be connected by 1 fewer edge than there are vertices. So in this case, you look at number 1, there are 5 vertices. There's only 1, 2, 3, 4 edges, 1 less than the number of vertices. There's 5 vertices and there's 4 edges. If you come over here to number 4, same thing. Same number of vertices, but only 1, 2, 3, 4. 5 vertices and 1 fewer, 4 edges. All right, a cycle. This is a definition. If you look on your word wall, it's just been introduced. A cycle is a graph, or in a graph is a path that starts and ends at the same vertex and does not use any edge more than once. Another way to determine that a cycle exists in a graph is there are multiple pathways between 2 vertices. So we're going to identify which arrow pathway describes a cycle. All right? So look at 1. We're going to start here, here, here. We went back to the same vertices. Notice it doesn't say every edge. It says any edge more than once. So that's why you have all these edges that weren't touched. And we'll look at this one. It goes here, 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 there, 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 there. And of course, I gave you the answers. 1 is a cycle. It starts at this top left corner, and it goes right and then to the middle, and then back up to that top left corner again. That's a cycle. And on 3, we start at the top right corner. We go down to the middle and back to the right corner. So those are both cycles. Notice a cycle is different from a circuit. A circuit, if you're not familiar, touches every edge, or it touches every vertex in the case of a Hamiltonian. In this case, we didn't touch every edge, did we? No, but we did start and stop at the same vertex. All right. Do either of the following networks have cycles? Okay, so let's look at them. In this one, can you start and stop at the same edge by following a single pathway without crossing an edge more than once? No, you can't. Same thing here. You would have to cross an edge no matter where you started to get back to that. So neither one of those cycles. Now, to answer the question, should they? That's a little trickier. You need to think about it for a second. The only way they should is if you were trying to reduce the number of edges. And there are some practical purposes for that, and we'll look into that here in a second. All right, so which of the following statements is true? Each of these graphs have a cycle. Is that true? I think we answered that in the last statement. No, neither of the graphs has a cycle. That is a false statement. If either graph had a cycle, an edge could be removed, leaving all nodes connected by another edge. Okay, think about this for a second. Let's say there was an edge here, right? One extra edge, right? And if we removed any of those edges there, would they all still be connected? Well, it depends on what edge we removed. If we removed one of these two, then it wouldn't actually be connected anymore. But if we removed any of one of these three, we would still be connected. Same thing here. If we put an edge here, as long as we only remove one of these three edges, we'd still be connected. But if we remove some of them, we might not be connected. So that's kind of an if. It is true, an edge, but it has to be a specific one. Cycles exist in every network unless all edges are removed. Well, that's not true. These are both networks and they don't have any cycles, so that's not a true statement. Redundancy makes a network more efficient, so cycles improve efficiency. Well, let's discuss what the word redundancy. Redundancy means it happens again. So a cycle is a redundant pathway between two vertices. So let's look at an example here. If there was an edge between this vertex and this vertex, there would be two pathways between the two vertex, from here to here, and then through this vertex following that path. That is what we call a redundant path. In other words, there's more than one. Now, efficiency means something completely different. Efficiency means that we are trying to reduce the amount of something to make it just enough, okay? So this pathway is efficient because all of the pathways are all the vertices are connected, but there are no additional edges necessary. So it's efficient if you have one fewer edge than you have vertices. There I go, making a mistake. Notice that the plural of vertex is vertices, not vertexes, like Coach Primo just made the mistake of saying. Anyway, so redundancy does not make a network more efficient. So cycles do not improve efficiency. They actually reduce efficiency. So that is a false statement. All right. Like I said, number 2 is the closest thing we got to it, and it's really not exactly true. It really depends on the edge you remove. All right. Here's a big concept. What does the existence of cycles tell you about the efficiency of a network? This should be really simple, folks. A cycle means that that particular network is what? It exposes an inefficiency of the network. Redundant pathways are inefficient. I'll just explain that in the last set of questions. Now let's describe how cycles are similar to an Euler circuit and how is it different. Okay, similar. A cycle is similar to an Euler circuit in that it starts and stops at the same vertex. It also touches edges only once. How is it different? Here you go. It's different in that an Euler circuit touches every edge, but a cycle does not touch every edge only once. Several cycles can exist inside a graph where an Euler circuit exists. Okay, so there's a difference between a cycle and a circuit. All right. Now let's write a step-by-step algorithm to convert an inefficient network into an efficient network. Now, if I were teaching, or if I was taking this course right now and I was taking notes, this would be something I'd want to write on my notes so that I have it ready on my cheat sheet to prepare for a test. An algorithm is a process or set of rules to be followed in calculations or other problem-solving operations. Step 1, look at two vertices on a graph. If there is a cycle that exists between them, we'll remove edges until only one pathway remains. Okay? Step 2, move to another pair of vertices where a cycle exists. And then we'll repeat step 1 and 2 until no cycles remain between any vertices. Then you should have an efficient network. Pretty cool algorithm, and it works every time. Oh, okay. We're going to apply this algorithm to the following inefficient network and indicate the number of edges in the final efficient network. Indicate which edges were removed by their letter label. So we have A through K. That means, if I'm not mistaken, there's 11 edges. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, I was right. Okay. So let's look between edge A, or the two vertices between edge A. So there's a cycle that exists between here, and also through here. So if we remove C, we remove that cycle, but we have other cycles, and we'd have to continue to do that until all the cycles were removed between these two vertices. We would remove all three of these until A was only connected. You get the point. And you continue using that process until you get only the edges available. All right. So this is one example of utilizing the algorithm to create an efficient network. Notice in this case, A is gone. But if you look carefully, you can see where the nubs are, where the vertices or the edges used to be. And doesn't take much to figure out that if you count the vertices, the edges will be one less than. Let's see, 1, 2, 3, 4, 5. There are 6 vertices, and there are 1, 2, 3, 4, 5 edges. Now we know it's an efficient network because there's one fewer edge than there are vertices. All right. I'm going to launch you with this, an aha moment. Let's talk about the aha moment. I'm not sure what it was back then. Can you recall a time when you had an alarming realization to a concept that before you hadn't understood? And by alarming, like it just pops in your head. If you've ever read about Archimedes, when he discovered that to determine the volume of a substance, you can put it in water, and the exact amount of volume of water, if the vat of water that it was holding, it would spill out, and that exact amount is how much volume that particular item has. When he discovered this, it was his aha moment. But it just so happened that he discovered this when he was taking a bath, and he ran through the streets yelling, "Eureka, Eureka!" And I think that's where the word streak came from, because he forgot to put his clothes on. Anyway, it is these moments that educators count as our greatest rewards. You can see it in our smiles when you get it, and that's true. When I'm teaching and I notice that a student actually grasps a concept that before they hadn't actually grasped, it's the reward beyond compensation that I can't explain unless you've actually been there. Anyway, there is a lesson for you in the Google Classroom. Go take a look at it and get it done. Y'all have a great day.